we should start by doing some trigonometry that we didn't get to last Friday. And that is to focus on the Pythagorean identity. Pythagorean identity. Based on the unit circle definition of cosine and sine, remember the unit circle in the plane centered at the origin with a radius of 1 has equation x squared plus y squared equals 1. Also remember that for a given number t that we can take to correspond to an angle with a radian measure t in such a way that this distance right there is t and the radian measure of this angle is t. That's what radian measure is. It's the same as that distance along the arc. The first coordinate of that point is, by definition, cosine of t. And the second coordinate of that point is, by definition, sine of t. And since every point in that circle satisfies the equation x squared plus y squared equals 1, that means no matter what t is, cosine of t squared plus sine of t squared always equals 1, no matter what t is. Understand that in both of these expressions, cosine of t squared and sine of t squared, it means, right there, for example, do cosine of t first and then square it. Over here, it means do sine of t first and then square it. Though more typically, we don't bother with the extra set of parentheses and we put the power of 2 right there and right here. You should never ever forget what that really means. Okay? It means what you see up there. Often, quite typically, people don't bother putting parentheses around the input for the t here either. But I like to do it whenever I can, remember to do it at least, to emphasize that these things are functions. And again, you find cosine of t first, then square, then add sine of t squared. And you always get 1 no matter what t is. This is an identity. Identities are different than equations, even though they both have equal signs. Equations, typically at least, are thought of as being things you need to solve for the unknowns. Here, you don't try to solve for t. It doesn't matter what t is, this works. For any value of t, you plug it in, you're going to get 1. To just take an arbitrary example here, if I compute cosine of 0.178 squared and then add sine of 0.178, it's got to be the same number, squared. Enter that, I will get 1. Okay, it doesn't matter that it's 0.178. It could be any number as long as it's consistent. Question? Yes, cosine of 0 squared is 1 squared is 1. Sine of 0 squared is 0 squared is 0. 1 plus 0 is 1. Yes, it holds when t is 1. If you graphed cosine of t quantity squared plus sine of t quantity squared, you'd get a horizontal line at 1. It simplifies to 1 for all values of t. No need to solve this equation. Very, very useful. And it comes up in problems, for example, like this. Suppose sine of t is, just to pick something that works out nice, negative 3/5, where t, if thought of as an angle, is in the 4th quadrant, say. Fourth quadrant. Question is, what is cos t? When I say it's in the 4th quadrant, if you think of it as I'm saying, if you think of it as an angle, its radian measure would put it in the 4th quadrant. If you thought of it as just a pure number, not necessarily thinking of it as an angle, its numerical value would be between, well, in degrees, it'd be 270 degrees and 360 degrees. In radians, that's between 3 pi over 2 and 2 pi. That's the same as 270 degrees and 360 degrees. The best way to figure out the answer to this question is to use the Pythagorean identity, as well as thinking about what quadrant this is in, and whether this cosine should be positive or negative. We want to find the cosine, so solve this equation for cosine by first solving for cos squared. That means cosine of t is, in general, plus or minus square root of 1 minus sine squared. And since you should know that cosine of t is positive, being the first coordinate of the stopping point on the circle, the bug, remember the bug? The first coordinate is positive over in the first quadrant and the fourth quadrant. Oh, so it's positive in the fourth quadrant. Cosine of a number between 3 pi over 2 and 2 pi radians is positive. So we take the positive square root. That implies take the positive square root. If we happen to be in a quadrant where the cosine is negative, second or third quadrant, then we take the negative sign. So you have to think about what quadrant you're in if you think of the number as an angle. So we do take the positive square root, and now we can go ahead and plug in the number -3/5 in place of sine, and get that square root of 1 minus, in parentheses, -3/5 squared. That's square root of 1 minus 9/25. 1 is 25 over 25 to get a common denominator of 25. 25 minus 9 is 16. Oops, that's a 25. This simplifies to +4/5. And by the way, in case you didn't know it, the square root of a fraction like this is the same as the square root of the top divided by the square root of the bottom, is another confirmation that it's 4/5. That's the best way to solve this problem. If you know sine of t is -3/5, and you know t is in the fourth quadrant, meaning it has this kind of numerical value, we always assume radians in this class unless told otherwise. We always assume we're dealing with the oscillatory functions that have a period of 2 pi here. That tells us we solve for cosine of t with the Pythagorean identity, and we take the positive square root because we're in the quadrant where cosine is positive. If we had been told t is in the third quadrant here, we would take the negative square root and we get -4/5 for the answer. Is there another way to solve this problem? Yes. You could take the inverse sine of both sides and then take the cosine of the result. However, you still need to be careful about quadrants in this case. Though, since the inverse sine function gives you an answer either in the first or fourth quadrant, it's less tricky here than it could have been. T is the inverse sine of -3/5. It's also okay to write that as the arcsine of -3/5. Inverse sine and arcsine mean the same thing. And remember, like at the end of class last Friday, this does not mean -1 power. I know that's inconsistent with calling that a second power. The notation is inconsistent. We live with it, okay? Because if you meant sine to the -1 power of an angle, like I mentioned last time, whoops, sine of an angle to the -1 power, we would not write this. Instead, we would either write this or this or this, cosecant theta. These are historical things that we're stuck with. Okay? Yes, sometimes math notation is inconsistent and confusing, but we're stuck with it. You want to get used to it. Likewise, cosine of an angle to the -1 power is either written like that or like this, or as secant theta. We want to find the cosine of t here. So you could now take the cosine of both sides. Cosine of t equals cosine of inverse sine of -3/5. It's going to work out okay in this case because of it being in the fourth quadrant and inverse sine giving us an output in the fourth quadrant in this case. You can solve this without a calculator, but it's a little tricky. You'd want to think about right triangles still and use the Pythagorean theorem. But let's just use the calculator. Cosine of inverse sine of -3/5, which is also -0.6, should give us 4/5. It should give us positive 0.8. Yes. That's 0.8. That's 4/5. But yeah, if I had changed the problem and said it was in the third quadrant instead of the fourth quadrant, first, second, third, over here in the lower left, that's where the cosine is negative. That's one quadrant where the cosine is negative. Second and third quadrant are the two quadrants where it's negative. So doing it with this method, again, I would have to use the minus sign from the plus or minus. What about this method? We would have gotten the wrong answer because the calculator doesn't know where t is, and it doesn't know what quadrant t is in. This would have been the wrong answer for the cosine. But this identity is still true. You'd then take the negative of this answer. T in radians, inverse sine of 3/5, is the value of t in radians. Oops, -3/5. -0.64 radians. That's in the ballpark of -30, -35 degrees, I think. I'll multiply it by 180 divided by pi. About -37 degrees. In a picture, the angle t is right around there. That's the angle t. And we just found its cosine is 0.8. That's the first coordinate of that point, 0.8. If it had been in the second quadrant, the third quadrant, it would have been symmetric across this axis. It would have been over there, and the cosine of it would be -0.8. So also something else we should talk about, the inverse tangent function. I guess that means we need to talk about the tangent function itself first. I'm anxious to get to inverse tangent, though. Tangent of t, by definition, is sine of t divided by cosine of t. That's the definition of tangent. Yes, it's TOA, opposite over adjacent, if you've got a right triangle as well. The hypotenuse from the sine and cosine cancels. The graph of tangent, it shouldn't be surprising, is periodic, but it doesn't look like the graph of sine or cosine. It doesn't oscillate in the same kind of way. It, in fact, has vertical asymptotes, which should be clear if you think about it briefly. You'd have vertical asymptotes wherever cosine of t is 0, because you'd be dividing by 0. Does bring up another issue. Just because you're dividing by 0 at a point doesn't necessarily mean there are vertical asymptotes. We will see very shortly, maybe even today. But this one does have vertical asymptotes where the cosine is 0, which happens to be at, for example, pi/2, 3 pi/2, 5 pi/2, 7 pi/2, odd multiples of pi/2, also including negative odd multiples of pi/2. Vertical asymptotes, and it is periodic. This just keeps repeating itself forever and ever. That's 5 pi/2. Excuse me, 3 pi/2. There's another one at negative 3 pi over 2. Not a one-to-one function. No, sine, cosine, and tangent, none of them are one-to-one. In fact, they're infinity to one. Very badly non-one-to-one. There are infinitely many lines, any horizontal line that goes through this more than once, in fact, infinitely many times. So it's very badly not one-to-one, so it definitely doesn't have an inverse function. Oh, unless we restrict the domain to being negative pi over 2 to positive pi over 2, not including the endpoints. And the inverse function of that would be the reflection of it across the line y equals x. So what would that inverse function look like? Turn your paper this way so that the red dashed line looks vertical. To help you do the symmetry across that line, the inverse function, if you do it carefully, looks about like this. That green graph is the graph of the arctangent function or inverse tangent function. Inverse tangent of x, or t, I'll call it. Also called arctangent of t. Maybe it's not good to use the same letter t for the input here because these are inverse functions, but we won't worry about it. I mean, yes, when we've got the same axes labeled and we're trying to draw them in the same picture, then it is probably best because of the reflection property. Just as the tangent function has vertical asymptotes at negative pi over 2 and positive pi over 2, so the inverse tangent has horizontal asymptotes at negative pi over 2 and positive pi over 2. Negative pi over 2 and positive pi over 2, illustrating that there are functions that can have two distinct horizontal asymptotes. Maybe you're used to rational functions and your teacher emphasizing they have a unique horizontal asymptote if they have one. And that is true for rational functions, but there are other functions, the inverse tangent, also called arctangent, being the most prominent among them, that can have two distinct horizontal asymptotes. Furthermore, it's also worth telling you that just because a horizontal line is a horizontal asymptote doesn't mean the function can't cross it. I'm not going to make a big deal of this, but the function f of t equals sine of t divided by t, for example, is a function where the horizontal axis is a horizontal asymptote, but it crosses it infinitely many times. It's just that because you're dividing by t, the oscillations get smaller and smaller in amplitude. And actually, this is an example of a function that, while it's undefined at 0, actually does not have a vertical asymptote at 0, even though it's undefined there, even though you put a missing point there on the t-axis. It's called the removable discontinuity, which is going to be a big subject for us starting on Wednesday of this week. Maybe even a little bit today. Okay, I'm not going to focus on this function much right now, but it is an example of a function that crosses its horizontal asymptote infinitely often. You can cross horizontal asymptotes. It's just that with rational functions, you don't typically cross them. Question?
So if tangent of t equals sine of t over cosine of t?
Sine of t would be tangent of t times cosine of t. Just multiply both sides of by cosine of t.
So it is cosine.
You'd have to multiply both sides by cosine, and then divide both sides by tangent to solve for cosine. Sine of t is tangent of t times cosine of t, and cosine of t would be sine of t divided by tangent of t. You got to do the algebra correctly. Technically speaking, these equations are only true for values of t where both sides are defined. In this one, it would exclude odd multiples of pi over 2. In this one, it would exclude odd multiples of pi over 2, as well as even multiples of pi over 2, which would be multiples of pi, because that's where the tangent is 0. There's always these technicalities about domains to think about, but in general, for most values of t, these equations are true. And I just got them algebraically from this one. Not something you typically use much, though. What's most important about this is the graph of inverse tangent does come up in applications. Okay, now it's sine and cosine. The ordinary graphs of sine and cosine come up in applications because they model oscillatory phenomena, periodic phenomena. How does the graph of arctangent come up? In situations where you've got some quantity that is slowly increasing from some finite value to some other finite value. And that actually comes up more often than you might think. And for calculus 2, arctangent turns out to be important for doing integrals. May get to an example like that in our class when we talk about integrals, but comes up a lot in calculus 2. You need the arctangent, inverse tangent function to help you do various kinds of important integrals. Okay. You can also use it to solve equations. For example, when does sine of t over cosine of t equal 5, which I could have written as sine of t equals 5 times cosine of t. Well, that's equivalent to tangent of t equaling 5. One value of t that works is the inverse tangent of 5. What is it? You'd have to approximate it with your calculator. Inverse tangent of 5 is about 1.37. It's got to be less than pi over 2. Pi over 2 is 1.57. This implies t as one possible value of t that works is about 1.37. Coming back to this red graph of the tangent function in here, what we've just did is we've just found that when t is about 1.37, then the output of this is 5. Okay, and I've been drawing it accurately over here. Okay, pretend I drew that accurately. This is not to scale. This is not quite right. Okay, this picture is not quite right, but that's the idea. 5 is not that close to pi over 2. This should be a little closer to pi over 2. I was just trying to quickly give you the idea of what we just found. But there's infinitely many others. If I add any multiple of pi to this, I'll get other answers for when tangent of t equals 5. But the inverse tangent gives you just one of them. Those are, to tell you the truth, the most important things to know about trigonometry for this course. What we did the last 40 minutes of class last Friday and what I just did today. There's plenty else to know about trigonometry. You might remember a bunch of other trigonometric identities like cosine of 2t and sine of 2t called double angle formulas. Actually, a couple formulas that are useful for calculus 2 are these. Cos squared t is 1/2 plus 1/2 cos 2t. And sine squared t is 1/2 minus 1/2 cos 2t, not sine 2t. These are important in calculus 2. Important for doing integrals in calculus 2. And again, they are not equations to solve. They are identities. They're true no matter what t is. Trigonometry is full of amazing, surprising identities. Identities are useful. So you want to know some basic ones and be able to look up other ones. Another question? It's related to something called the double angle formula, but technically it's not one of the true double angle formulas. Go ahead and make that remark here. You can look up the double angle formulas if you want. Related to double angle formulas.